Today we'll be talking about moving conductor in static magnetic field. In static magnetic field. This is actually one of the three topics in usually in time-varying Maxwell equations. It covers moving conductors in static magnetic field, also static conductor and time-varying magnetic field, and the third one would be obviously both combined, which is moving conductor in a time-varying magnetic field. So today's lecture will mainly be focusing on moving conductor in static magnetic field. If we take a wire, for example, let's start with this drawing, and you have a magnetic field that's going outwards, going out of the paper, and with a magnitude of B naught with at the Z direction. So if you draw the X and Y coordinate, you get the Z pointing out of the paper. So this is where the magnetic field is pointing out. As for the wire, it will have a length L, and since we're working with moving conductor, we assume the wires going in the X direction with a velocity of u. So the velocity u, the wire is moving at a velocity u in the X direction, and the length of the wire goes along the Y dimension, and the magnetic field goes out of the paper. Now let us say that this wire's we obviously are moving, the wire is moving across the, it will be crossing that magnetic field as time goes by. The units of the velocity is meters per second. So over time the wire will be moving and will not stay in one spot. Now the conducting wire obviously contains free electrons. We know that the magnetic field, so we know that the magnetic force Fm acting on a charged particle Q, we can say, with a velocity vector u in a magnetic field. In magnetic field B is as follows. Fm equal the charged particle u cross B, which is the velocity crossed with the magnetic field. So we also know that this magnetic force is equivalent to the electric field, or electric force, you can say electric force, that would exert, that would be exerted on the particle by an electric field. EM. In other words, we can relate the electric field component, this one, to our magnetic force component. We do the following. The electric force, so electric force equals to the charged particle multiplied by the electric field, the motional electric field, and which is also equal to the magnetic force. Therefore, we can deduce from that the motion electric field is equal to the magnetic force over the unit charge, or you can say the charged particle. We know what is important to note here is that the motional electric field is basically perpendicular to the plane containing U and B. U, which is obviously the velocity, the direction of the velocity with its magnitude, where the wire is moving from this diagram, and the magnetic field. So the motional electric field is perpendicular to the plane containing these two vectors. So for the wire shown here, for this wire shown here in our figure, EM is going downwards in the direction of negative y, and the reason is the EM is perpendicular to the plane containing the Z, which is the magnetic field, the B and U, as I said. So motion electric field is perpendicular to the plane containing U and B, and U is along the x-axis, and the Z is the magnetic field is along the z-axis. And doing the cross product, which I will probably demonstrate at the end of this mini lecture, the right hand rule to obtain the U cross B, the direction. However, for now, if you can see it, that's fine, you can skip the end of this lecture. However, if you don't know it, you can stick around, but I'll briefly discuss this with using my right hand. If I'm trying to go from X to Z, you have to imagine the Z axis in your mind, and what happened is you try to curl the four fingers towards that Z, which is outside of the paper, and then obviously you see, if you turn it this way, if I stand this way it's probably better, so the X is this way and I'm going outwards to the Z axis, and I see my thumb is pointing in the minus Y direction, and this is how I use the right hand rule. That's how we know the motion electric field is pointing downwards. So now the magnetic force, yes, actually the recorder stopped recording while I was writing these extra stuff that you see here. So I'm keeping them here, and I'll just say them. I'll just say what they were. Basically, we were talking about the motion electric field being perpendicular to the plane containing U and B, which is the velocity, the direction of where the wire is going, and the is moving, and the magnetic field, direction of the magnetic field. So basically, what I was saying here is the fact that magnetic force is acting on electrons in the wire, causing them to move in the direction of minus EM. So basically, we all know that the magnetic flux is acting on electrons, and electrons are negatively charged. So what happened in this case, if we go back to our magnetic force equals the charge particle and U cross B. Now that's the direction we were talking about earlier of the motion electric field is going in the minus Y direction due to the U cross B. Now if the charge is a negatively charged particle, which is in this case it's acting on the negatively charged particles in the wire, so this causes them to move in the direction of the negative motion electric field. And what's important to note here is that this in turn induces a voltage difference between ends 1 and 2. So between ends 1 and ends 2 you have a voltage difference. So what does that actually represent? The end 2, which is this one, this end of the wire, being at the higher potential. Obviously, due to the fact that the electrons now are moving in the Y direction, so from 2 to 1, and it goes from a high potential to a low potential. This means the end 2 is the one with the higher potential. Now what's really important from all this is the fact that this voltage is called electromotive force, or in short VEMF, or sometimes some books refer it as just EMF. And now due to the fact that the conductor is moving, some also books use M to represent motion. And if the conductor is static with a time varying magnetic field, usually it's TR here for transformer electromotive force. Now what is this defined mathematically? The electromotive force, motional conductor. Now since we're working with this example 1 and 2, so voltage, it's really the voltage of 1 to 2 is equal to the integral of, as we know from previous studies, it's the integral of the motional electric field multiplied by the time of rate of the length L, of the change of L. So which really equals to 2, 1. We know the electric field, since magnetic force equals to the charge times the motion electric field. This will mean that the motion electric field is equal to U cross B, and this is exactly what I'm writing here, U cross B times dl. Now for this conducting wire, what would dl be? Usually dl is looked at the part of the wire that crosses the magnetic field. So where the charges cross the magnetic field. Now obviously the charges are in the wire, And since this is moving at the rate of meters per second, over time, the spot where this wire is changes. And this means that where the wire is located at is what we have U cross B. In other words, or you can look at it excuse me, you can look at it this way. The electromotive force only exists at the points where the wire crosses the magnetic field, the charges. So everywhere else there's no electromotive force, and due to that the VMF only exists in the rod, in the place where the Y direction. So DL is really equal to Y direction dy. Now, so we're trying to solve this. So the VMF will now be equal to 2, 1. U naught X. The wire is going in the X direction, so X hat U naught being the magnitude of that vector U crossed with B naught Z a hat, and all in the Y direction. Note here that even though the velocity is 1, 2, we start with a 2, 1, and that is exactly what we were talking about. I was talking about earlier about the electrons moving in the direction of the negative motional electric field, which is this case. Hence, it's from 2 to 1. Although the motional electric field is going in the negative Y direction, the fact that the electrons are moving now, moving in the other direction, we integrate 2 and 1. Sometimes we refer this sometimes as which is actually Lenz Law. We want to satisfy Lenz Law. However, to my students, sometimes I try not to focus too much on that term, because usually in Lenz Law we focus on time varying magnetic fields, if it's increasing or decreasing. I'll probably say this quickly here. For example, if you have a wire and magnetic field going through that wire, this produces the current going this way using the right hand rule, and assuming that this magnetic field is increasing, and we need an opposing induced magnetic field to the increasing magnetic field. Increasing magnetic field, because it's going that way, the increasing will be this way, and then you want to oppose that increasing magnetic field, you go the opposite direction, be induced, and this will create its own current, I induced, and which flips the voltage difference here from how it used to be before, from the magnetic field. It's a plus here, minus here, and now with this induced current. Again, the recorder stopped, so I'll continue with what happened. I was talking about the magnetic field is increasing. You end up with a opposing induced magnetic field, which in turn gets its induced current, and it flips the voltage difference that existed before from a plus minus from this current to a plus here and a minus here. So now this induced current goes through to high potential, goes from a plus minus here to a plus minus there. So plus will be here now and minus will be up here. So that's usually, this is what Lenz Law talks about, which is really it shows that the induced voltage acts in such a way as to oppose the flux producing it. However, now that we're talking about not changing magnetic field, we're talking about static magnetic fields. I usually go on with the fact, I usually talk about the fact that the magnetic force acts on these electrons in such a way that it causes them to move in the direction that is opposite of the motion electric field, which is now you reversed of it. So bring an example about this just to make things clear. If you have the same thing, I'm not going to change anything from that initial one. So I drew it a little bit weird, but it doesn't matter. So you get going through the same thing, X, Y, and the magnetic field going in the outwards, Z direction. Let's call this point 1, point 2, 3, 4. So the electromotive force here will be equals to the voltage across 1 and 2 and equals to the voltage across 4 and 3. Sorry, 4 and 3. So from the equation we've done earlier, which is the motion electric field integral, and over dl. Now the integral here, just I was explaining earlier, that the electrons are moving in the direction opposing or opposite of the negative of the motion electric field. So the electric EM is going downwards in the minus y from 4 to 3. Now it's going from 3 to 4. So the electron moves from 3 to 4. So from 3 to 4. So you see the flip here. And now what's dl? Obviously we described that earlier as dy hat dy, because this is where the charges are. So we end up with 3, 4, x hat, the direction of the motion of that conductor, cross with z hat, the direction, the magnitude of the direction of the magnetic field and its magnitude, and dy is equal to y hat dy. Now what's x cross z? Again, using the right hand rule, you have x cross z. The same example points to the negative y hat. So this will give us x cross z will give us negative y hat. So if you solve this, you end up with minus u, magnitude of the velocity, and magnitude of magnetic